So in this video, we want to look at a bunch of different, start looking at a bunch of different derivative rules. So we want to look at rules for specific types of functions, some different special functions, what their derivatives are, what do we do when we have a product of functions, what do we do when we have a quotient of functions, different combinations of functions. So these won't all be in this video, but these are the next several videos we'll look at. So this first video, I want to look at a very special one, maybe probably the most common one. So this is called the power rule. So some derivatives we've already seen. Okay, we've already seen that we could say the derivative of x squared is 2x. Right, we've seen that the derivative of x cubed is 3x squared. Some things we haven't seen, the derivative of x to the fourth is 4x cubed. So maybe if you look at this for a minute, you might start to see a pattern here. Okay, so just take a moment just to look at it and see if you can find a pattern. Finding patterns like this will be really important towards the end of this class, so it's a good thing to practice. So, in general, what you might notice here is that if we have something x to the nth power, where n is really any number, we like to focus on integers, but it doesn't need to be an integer. There's only a couple of restrictions on what it could be. But anyway, if we look at this function, the derivative of this function, we get n times x to the n minus 1. Okay. So you kind of pull that power down and then you subtract 1 from the power. Okay. So if we want to find the derivative of x to the 27th, it's going to be 27x to the 26th. Okay, so this is the power rule. So showing the power rule, the proof of it, I'm just going to do like a sketch of the proof, just like kind of the main idea of the proof. Not that the proof is difficult, but you just have to use what's called the binomial expansion, and I'll kind of show what the idea of the binomial expansion is. So let's look at the limit as h approaches 0 of x plus h to the n minus x to the n over h. So specifically, you want to find the general formula for the binomial expansion of x plus h to the n. So we won't get into all that, but essentially the idea here is that the first term is going to be x to the n. The second term is going to be n x to the n minus 1 times h. Okay, and it's just going to keep going like this until the last term is h to the n. And then we have minus x to the n over h. So these terms will cancel out, right? Now all this stuff in the middle, it doesn't really matter too much because the important part is that all of them are going to have at least one h. Specifically, this is the term with one h, and then all the other terms are going to have at least an h squared or higher term in it. So what's going to happen is that when we cancel those h's out, right, so we're going to cancel them out, we're going to be left with n x to the n minus 1 plus h times a bunch of stuff, right? And when we let h go to 0, all that stuff is going to be 0. So this is going to 0. So we have n times x to the n minus 1. Okay. So the reason that we typically put the restriction that n must be a positive integer on here is because this binomial expansion only works if n is a positive integer. But there really is no restriction on what n can be. For this proof, there's a restriction, but in general, you can prove it in other ways that this will work no matter what n is. I think I said a second ago that there was some restrictions, but the restrictions are on the integral side of it, not on the differentiation side of it. So yeah, there are no restrictions at all on this. So we can just go ahead and look at some examples. Whoops. So some that we've already seen, like I said, we just saw x squared and we just saw x cubed. We also saw 1 over x, right? So let's do this with the power rule. You might not think of this as a power rule right off the bat, but it is a power, right? This is x to the negative 1. So this means this is negative 1 times x to the negative 2, which is negative 1 over x squared, which is exactly what we got as the derivative before. Same with the square root function. Okay. This is actually x to the 1/2. So that means that this is actually 1/2 x to the negative 1/2, right? Because 1/2 minus 1 is negative 1/2. So that's 1 over 2 x to the 1/2 equals 1 over 2 root x. Okay, so that's why this rule is so useful, is because we can do any there's just so many functions that we can express in terms of these powers that we can then apply this rule to. So let's look at some other kind of strange ones. What about just x, right? This is x to the 1 power. So this would be 1 times x to the 0. X to the 0 is just 1. So this is 1, which is what we would expect because it's the slope of that line, right? 1. Okay, what about x to the 0? Okay. First of all, what is x to the 0? X to the 0, we just said, is equal to 1. So we're really looking for the derivative of 1. So what is that? Well, we can do the derivative of x to the 0. So this is equal to 0 x to the negative 1, which is 0 over x, which is 0, right? Of course, here we have the restriction that x is not equal to 0. But regardless, we're really just showing that the derivative of 1 is 0. And 1 is not special here. You can show that the derivative of any constant function is 0. So that's relatively easy to do just using the derivative definition. Okay, so the only thing I want to note here is that for something like 2 to the x, don't get the power rule confused with this, because there is a power here, but the variable is the power now. So this derivative is actually going to be quite different. And we'll look at this in a minute, but this is going to be 2 to the x times the natural log of 2. But it's not going to follow this power rule in any shape or form. Even if you have something like x to the x, this is also something that's very specialized, very different. This one, you actually want to rewrite it. This is kind of a weird little trick where you rewrite it as e to the natural log of x to the x, because e to the natural log, remember, cancels out. So this is equivalent. So then you have e to the x natural log of x, and then you can apply two things called the product rule and the chain rule. But that's getting way ahead of ourselves. I just wanted to show basically that just because it has a power in it doesn't mean it follows this rule. It's specifically when you have x to some power, some constant power.